I'm Max Fortin. I'm presenting characteristics of a reacting jet and crossflow at elevated pressures. A quick introduction to axial stage combustion. It's a type of combustion that allows a reduction in NOx and CO2 emission. It currently achieves this utilizing a mixing technique called jet and crossflow, which allows for more efficient mixing of the fuel jet into the crossflow. There's been plenty of research done on jet and crossflow, but there exists a significant knowledge gap once it comes to higher pressure conditions, which are more relevant to industrial and aerospace applications. The current applications for this study would be reducing emissions and increasing engine and turbine efficiency within energy generation fields. Starting out with the testing rig, we first start off with a main burner stage, which has a pressurized air fuel mixture. In this case, we're using methane, a hydrogen pilot, and dilution air. The air fuel mixture is ignited with a spark and is kept stable by that hydrogen pilot. The burning products pass through this mixing section and exit out into this test section, which has windows for optical diagnostics. A 4mm jet at the top acts as the jet in the jet and crossflow. The combustion occurs and then it exits out the choke area, which back pressures the system to 5 atmospheres currently. So we were trying to find with this experiment how different jet penetrations into the test section, or how far the jet actually goes into the flow, relates to the momentum flux ratio. The momentum flux ratio is how much momentum the jet has in relation to the crossflow. As you can see, we tested at multiple different momentum flux ratios ranging from 0.5 to 107.8, and we found varying jet penetration distances from 0.13 to 1.47 inches. The effect of this is, as can be seen in Figure 1 and Figure 2, where the lower jet momentum flux ratio, the 73.8 case here on the left, versus the 107.8 momentum flux ratio on the right, shows that the flame stabilizes in the leeward shear layer, which is a lot less stable and prone to blowout when compared to the stabilizing in the jet core. It allows for a much more stable flame that is able to continue for much longer when compared to the lower momentum flux cases. The CFD, or computational fluid dynamics simulations, were performed in conjunction with this experiment and shows that at a momentum flux ratio of 10 and a momentum flux ratio of 30, 10 being on the left, 30 being on the right, backs up the findings from the previous cases, showing that the high momentum flux ratio stabilizes a lot better in the jet core rather than the shear layer underneath the jet. So the conclusion and the takeaways from this experiment is that higher momentum flux ratios typically correlate to a much higher jet penetration. A higher jet penetration allows, or an optimal jet penetration allows for a much better stabilizing regime, which allows for better, less blowout on the flame.